Last week, security researchers disclosed a new exploit in Apple M-Series silicon that they called GoFetch. And normally, I'm not a security researcher, so I really don't have any opinion on how bad this exploit is or anything like that. But for people like me who like to study microarchitectures to learn how they work and to be able to program them efficiently, this paper was actually really interesting even outside of the security context. The reason for that is they did a lot of microbenchmarking and determined how a particular part of the Apple silicon worked, about which very little was known before. And that part is called the DMP, or Data Memory Dependent Prefetcher. Now, I thought this was so fascinating, I wanted to do a video covering what they discovered about it and how it worked, because it's kind of a brand new thing that's happening in CPUs. M-Series is some of the first CPUs to have it. So this is a new thing that's happening in CPU design, and I want to be aware of how it works. So that was really cool to learn about that. And I want to share that with you, but also, like most times when I go over and read some of the security research literature, it's just fascinating stuff because they're fundamentally doing a bunch of things that are not what we normally think about on a daily basis. When the rest of us go to program computers, we're not trying to think about how to use all of this stuff together to create a way to get at secret information. So they're just doing so many different things that we're not used to. I found that part fascinating as well. The paper in which they describe all this is actually very good. It talks about all of it, but it's very, very dense, and it relies on a bunch of sort of outside knowledge that you'd have to crawl all the references to get. And so I'm also hoping to kind of make the paper a little bit more accessible and explain how the whole exploit works, just so you can gain an appreciation for it and get a foothold in there if you do want to read more. So let me go through the whole thing. And again, just saying again, I'm not a security researcher, so I don't have an opinion on the severity of this exploit. I'm really interested in the technical details, and I think there's so much great information in the paper, even if you don't care about the security ramifications at all. So what is a data memory-dependent prefetcher? Well, normally what happens in a CPU, you effectively have the register file of the CPU where it's actually storing data it's working with directly. And then you have a series of caches. In this case, the ones we care about are the L1 and L2 caches. And these are, things designed to hold little pieces of memory so that you don't have to go all the way out to main memory, or a slower cache in some cases, to get the data, right? That's what they're designed to do. They're designed to decrease the latency of memory fetches or increase the bandwidth, usually both. So when the CPU goes and requests some memory, it's actually usually requesting it from the L1 cache, which then requests it from the L2 cache, which then requests it from main memory, right? But the idea is that once it gets it back, it stores it in these caches so that when it wants to access that same piece of memory again, it doesn't have to go ask for it again. That's the standard idea of a cache, and everyone understands that from software as well. Even if you've never looked at microarchitectural details, you know how a cache works. You ask for something, it saves it, so the next time you ask for it, it's faster. Well, hardware, when they're designing CPUs, they want to try and get as much mileage out of these caches as they can. So they don't tend to leave it at that. They don't just say, well, wait till the user, the code requests something, and then we'll cache it. What they try to do is what's called prefetching. Prefetching is when they try to get memory moved into a cache earlier than anyone actually asked for it. Now, there is such a thing as software prefetching, which is when you do actually ask for it. You basically give hints in your code and say, I'm probably going to go look at these addresses at some point. Maybe you should get them filled in. So in that case, that's not really guessing. You're actually telling it. But hardware prefetching doesn't work that way. Hardware prefetching is when the actual CPU itself studies the pattern of memory accesses that you are doing, so these accesses when you're asking to bring new memory in. It looks at those series of addresses and tries to guess what the next addresses you might ask for would be. Now, to understand how this might work, think of something like when you iterate over an array. So you've got some big array of data here, and in order to make this kind of a system efficient, as you may or may not know, depending on how much you study these sorts of things, they tend to move in chunks. So when you ask for something, you tend to move at least 64 bytes at a time through these caches, sometimes 128 bytes, depending on the circumstances. And we'll talk about that in a second. So normally you move in these 64-byte chunks. So when you ask for some memory, you actually are getting a whole 64-byte chunk, at least, moved into the caches. And then you can use smaller parts of it to move those into the register file if you want to. This is all hidden from you. You don't actually know this is happening other than by observing like timings. So if you're going to go iterate over an array, that array, when you access it, when you first access the very first element of the array, what's actually going to happen is some amount of that is going to get pulled into the cache. For example, the first 64 bytes of that array might get pulled in, which could contain several members. And then you're going to kind of iterate through those members, touching the data, right? And then when you go to access the next one, it's going to pull in the next 64 bytes, right, into the cache and so on. Well, when you're doing this, assuming that the array is large, which is precisely the circumstance where the CPU might want to speed it up, it's kind of dumb to just wait for that. If the CPU can tell that you're just asking for chunks one after the other, a hardware prefetcher can step in and say, I see a pattern here. I see you getting cache lines, right? These are these little things called cache lines. That's what we call the 64-byte chunks. Again, don't know the sophistication of everyone watching, so I apologize if this is repeating things that you already know, but just so you know. We call these cache lines with the 64-byte chunks. Each cache line that you ask for, it's going to look and say, oh, they're just going in a line. Let me just start pre-filling those into the cache because I'm pretty sure that who's ever doing this array access is just going to plow through the entire thing, right? It's going to keep going, and we're going to get better performance by asking for those things early. Now, hardware prefetchers can be fairly sophisticated. They can do more than just guess that you're going to use things right next to each other. They can look and see if you're using a particular stride pattern, like you ask for one cache line here, and then you ask for one here, and you skip one. They can do more sophisticated things as well, so it's not restricted to just this. But it was, up until the DMP, restricted to basically that. Looking at addresses, looking to see if there's a pattern, and then guessing what the pattern would be based on the addresses. Now, the DMP, for the first time, is adding something to this hardware prefetching scheme. Instead of only looking at the address pattern, a DMP takes the very unusual and interesting step of looking at the actual data that comes back. So before, it was looking at these addresses. These addresses look like they go in order. But it was never looking at the values, the things that were in the array. Now, normally, if the array is just a bunch of numbers that you're adding together or something like that, or a string that you're looking through, that's fine. There's no benefit to the prefetcher to looking at the data that's actually contained in there. But what if, instead of data like that, what's contained in the array is actually pointers? What if there's just a bunch of pointers here that point off to objects or something like that? Like, imagine some C++ code where you knew a bunch of objects and you stick them in an array that you iterate over. Well, now the operation that you're doing probably involves using the data that's in those objects. Maybe making virtual calls on them, maybe looking at information in them. Who knows what it's going to do? And so now the memory pattern, in addition to just reading this part, which the hardware prefetcher can do quite well, there's all these unrelated memory blocks, right? There's all these unrelated memory blocks that are completely unpredictable. They could be anywhere because the general purpose allocator that allocated them just stuck them wherever it had room, probably, right? So now you can see why something like a DMP makes a lot of sense. If the hardware prefetcher can look at the data that you're actually using, it can see whether or not it thinks those are pointers in there. And if they look like pointers, asterisk on that, because how does it do that? We'll see in a second. If they look like pointers, then it could prefetch the destinations of those pointers, potentially dramatically speeding up the process, because now it can prefetch all this stuff and have it waiting warm in the cache for you, so it doesn't have to wait for you to actually ask for it. So this is a way of speeding up things that hardware prefetching previously couldn't speed up, like arrays of pointers or linked lists, right? Something where you have to load and then look at the data in there to know where to load next. A DMP can help address those speed up. Like it can basically provide speed ups where none were before. So how does this one actually work? And this is what I think is the most fascinating stuff in terms of general use in the GoFetch paper. How does the DMP in Apple series silicon work? because there's actually several interesting aspects of how they implemented it, and it's just really good to know, okay, here's how the machinery is working now. So, like I said, cache, they move, when they move things through caches, they operate in cache lines. These are 64-byte chunks most of the time, but sometimes they're 128-byte chunks. Now, the reason I say sometimes is actually it's not because of some other random situation. That's actually because of literally this very silicon. On Apple M-Series silicon, apparently, because I don't work on that silicon hardly at all, but apparently the L2 cache is actually 128 bytes per cache line, whereas the L1 is 64 bytes per cache line. What that means is that when something comes into the L2, it actually comes in as a bigger chunk, right? It comes in as 128 bytes, and then only some subset, like one half, either the high or low half of that, will actually come into the L1. Now, maybe both will, right? It could be that both do, but if they both do, they're coming into different places in the L1, right? It's not moved as a single chunk, and they might not. So you can pull in just one half of it, right? So this is working at a smaller granularity than this. That's not that relevant for this particular GoFetch exploit, but that is an interesting thing to know about how the M-Series caches work. So again, good piece of information to be found out just from reading this paper. Now, when this happens, the DMP is actually involved in when the L1 cache is filled. So you imagine these 64-byte, although they're 128 when they first come in here, but they're 64-byte, blocks, which we call cache lines, moving in to the L1 cache. When that happens, that is what apparently triggers the DMP to look at what is in the cache line. And it has a couple ways of doing this. First, what it does is it considers this cache line only in the scheme of 8 aligned pointers. Now remember, we're in 64-bit computing, right? That means that a pointer is 64 bits, that's 8 bytes. So inside a 64-byte cache line, 64 divided by 8 is 8. So we have exactly 8 aligned pointers, right? Now, this does imply, as I'm saying this, yes, the DMP will not look for unaligned pointers inside a cache line. It will just look at the 8 aligned slots, and it will ask, are any of these things pointers? Do they look like pointers to me? Now, it's pretty easy to say, well, you just look at a slot, and then you look and you say, okay, this expands out, and this is 8 bytes here. Is it a pointer? If you have some kind of debug information, maybe you know because you know it's a pointer. How do you know it's a pointer if you're just some hardware that's running it with no idea even what program you're running, right? You don't know anything about it. How do you know if this thing's a pointer? Well, what it does is it makes the following rather interesting assumption. It says, I know where this data came from, right? Because this was part of some process where there was a memory address, right? And this was a virtual memory address. So there's a virtual memory address in this process's address space. And when I filled in this L2 line, I know what virtual address I was looking for. So when I pull something into the L1, I also know which virtual address I was looking for. And I know, therefore, the virtual address of this line. What I could do is say, well, if I assume most of the time that people are using allocators, those allocators are probably allocating large chunks of memory and then sub-allocating out of those. Most of the time, one piece of memory will only point to another piece of memory that's in some fairly reasonably sized region around that memory. It's not that likely that most of my pointers will go from one large chunk of memory somewhere in the system to some completely distant, completely unrelated chunk. Now, it will do that in cases where you're manually allocating memory in specific patterns using base addresses or doing some kind of, file mappings and all that sort of stuff. It could always happen. But in terms of a heuristic, that's what they're guessing. They're saying it's probably somewhat local. So they say, let's consider something a pointer if the place where the pointer is stored is in the same 4 gigabyte region as the place the pointer is pointing to. Now, why 4 gigabytes? Well, if you imagine splitting an 8-byte pointer in half, we have 32 bits on this side and 32 bits on this side, right? That's 2 to the 32, or 4 gigabytes in the bottom part. So we're basically saying if we throw that away And then we say if the top 32 bits of this address match the top 32 bits of this address, then it's probably a pointer. It's probably something pointing from one part of that 4 GB address space to another part. Again, this is just a guess. Now, there is a little caveat here if you want to get the details right. It actually, if you think about this is 4 bytes, right? It's 32 bits. The top 8 bits, or top byte, right? This top 8 here. Technically, in ARM processors, there are ways to use those top 8 bits for things other than the pointer. This is just a way that ARM can be set to work. Intel actually also has a version of this. And the reason for this is because most of the time, if you're in 64-bit computing, you don't need all 64 bits of address space because that's just not a realistic thing to have in a system. So when they're contemplating system design in ARM, they're thinking, well, you don't need all 64 bits of a pointer. So some things like garbage collection schemes can benefit greatly in terms of efficiency by using like the top bits of a pointer for some kind of information. So you're actually allowed in ARM to use those top 8 bits for other things if you want. So in order to support that kind of behavior, apparently, and again, this is just stuff that the researchers figured out by micro-benchmarking, which is awesome. Apparently, when the DMP is looking for pointers inside a cache line, it also will ignore the top 8 bits. So it's really doing 24 bits, not 32 bits, and comparing the sort of this middle 24 here, ignoring the top 8, ignoring the bottom 32. If this 24-bit pattern right here matches that exact same place in the address of the cache line, again, these are both virtual addresses, then we say it's probably a pointer. And then we go ahead and we prefetch that. So we just say, I think they're probably going to access it. Let's go warm the cache. We'll prefetch the cache line that points to. Now, there are some things they wanted to do here to prevent over prefetching, right? So that's one thing, looking at the cache line and saying, well, I'm going to try to make sure they're actually pointers. Because if I was just to prefetch every single one of these slots as if it was an address, well, that's not very good because probably lots of them aren't addresses you're ever going to use. They're just data. Like, could be a float is stored here, and you wouldn't want to fetch that as an address. It's going to totally be wasteful. So instead, they're going to do this check to see if they're pointers. That's one way they try to limit the number of things they prefetch. But there's 2 other ways they limit it as well. The next one is they keep, and again, this was empirically determined by the researchers, which is awesome. They keep a 128 pointer sort of rolling buffer that stores the last 128 pointers prefetched via this scheme. That way, if it loads multiple cache lines that are all pointing to the same places, you won't overfetch those or waste time refetching them. And furthermore, you won't try to refetch things that probably already just got brought into the cache, right? You're not going to waste time on things that someone probably already prefetched. So this is sort of like a window to prevent overfetching or over-refetching, if you will. So every time it does actually go and fetch one of these pointers, it inserts it into this 128 pointer rolling window so that it won't overfetch things that it sees multiple times. But that's not all. It also does one more thing, and this one's actually pretty critical for the exploit in question, so this is pretty interesting as well. When this procedure happens, something moves into the L1, it goes and looks at the cache line, thinks of it as 8 little aligned pointers, sees whether or not they match the address of the cache line in the correct bits here, look to see whether they don't hit this 128 lookback buffer, and fetch it. When it does that whole process, it also tags the cache line. And it tags the cache line apparently in L2, actually. So when the cache line comes in and it does this scan, it tags it, and it tags it such that it will not be rescanned again the next time it gets brought into the L1 cache because it appears to tag it actually in the L2. Right? It puts that tag on it in the L2. So even if it gets evicted from the L1 cache, so it's not there anymore, but it remains in the L2 and never gets evicted out of the L2 cache, the tag will persist, and if it comes back in to the L1 cache at some point, it will still be considered to have that tag, and that tag will prevent it from being scanned. So this is, the researchers call this a do not scan hint. And this is basically a way of saying, look, only scan a cache line once when it comes into this scanning process, and never scan it again unless it actually goes all the way out, right, of the L2 cache. So that's how the actual DMP works, at least as far as we know. And again, all of that basically is thanks to these security researchers. There was some previous work that they referenced called Augury, which was a paper that did figure out some of these things, but it didn't get all of them. And so this paper is the first time that it seems like people have really worked it down to the bone. And we now know, like, okay, this exact process appears to be happening inside the M-Series Silicon DMP. So this is great, and this gives us a lot of insight into what will happen in the prefetcher when we're running code. Even if we're just thinking from a performance standpoint, we know that if we have pointers in the aligned slots when these things come in, the first time it goes to the L1, it will scan it if it points inside the same 4 gigabyte region, right? And then it won't do it again until it gets evicted from the L2. And that's pretty easy to actually remember. So really good stuff here. But as interesting as that is, you may also be wondering, well, how does this end up being an exploit? Like, what could you do? All it's doing is looking at your data, looking for pointers and fetching the pointers, which is the same thing you were going to do, right? Like, you were probably just going to go through these pointers and fetch them anyway, so how could this possibly cause a security exploit? So what I'd like to do now in the second half of the video is, after I go ahead and snap my fingers and erase this board because we're out of room, I'd like to go through how the exploit actually works, because that in and of itself is really quite fascinating. It doesn't really give us much information in terms of performance programming or anything like that, but it is just really fascinating to see. So if, like me, you find going over to other people's literature and reading sort of about what they've been working on fascinating because they're pursuing totally different avenues, I think you'll really enjoy this because, man, it is a really cool exploit, and it involves so many levels of thought of like what you can do. It's just very fascinating. So let me go ahead and clear the board now, and we'll go over that. Okay, so how does a DMP create a security exploit on M-Series Silicon that's new? Like, what's new about this? Well, the type of attack, broadly speaking, if we go all the way out to the highest level of, like, categorizing attacks, this is a timing attack. It's an attack that uses the measurement of the amount of time that has gone by in some kind of an operation in order to determine some kind of a secret value or piece of information that is not supposed to be disclosed to the outside. So you can imagine, for example, on your M-Series Silicon, you are running something, typically in the security literature, they call something the victim process if it is the thing that is going to be attacked. Then you've got some attacker process that you have created, and its goal is to compromise this in some way, to have the victim process disclose some information or something like that that's not supposed to. So inside this victim process, there's usually something that you want to get at, like a private key. And maybe this victim process, for example, you send it a message, it encrypts it using the private key or something like that, and gives you back some public information. Or maybe it even doesn't give it back to you, who knows? But the point is, it's doing something with the private key. Now, usually you're walled off, right? You can't actually access this private key. For example, the operating system has some kind of memory partitioning in place so that you can't access it. So the private key is opaque to you. But what a timing attack does is it says, well, if the victim process is ever written in such a way that its execution speed for some operation it does that we can watch depends on the value of the private key, we may, by watching it for a while, be able to determine what the bits of that private key actually are just by looking at variations in the timing. This is generally called a leak or leakage. It's the phrase that they use for when something is not actually disclosing literally the value that it was supposed to protect. It's not telling you what the private key is, but there's some information leakage that someone could use to reconstruct that private key. And in this case, it's time, the amount of time taken. So this is a timing attack, and you can sort of maybe start to think about, okay, well, I can see why something like the DMP might be implicated in a timing attack, because what is a cache if not something that speeds things up? So if there were some way to use the DMP as some kind of an attack vector to get the victim process to do something faster or slower or who knows what, right? we could use the time difference invoked by the fact that the DMP has pulled things into the cache or not pulled them into the cache, as the case may be, to leak information about what this private key actually is. So how does that work in practice for this particular exploit? How does the DMP actually create a situation where time can tell us something that we're not supposed to know? Well, if you imagine two things running on M-Series silicon, if they're both running on a performance core, which is the only case we would really care about in this case because the DMP apparently doesn't really exist on the efficiency cores of M-Series silicon. So in order for a DMP exploit to be implicated, both the victim process and the attacker process both have to be running on performance cores. Crucially, they don't have to be running on the same performance core. So they can actually be running on completely separate cores, which you would think would be more isolated, but in this case, it doesn't actually matter. They just have to both be performance cores so that the DMP is implicated. Now, what is the problem here? Well, even though obviously Mac OS and the CPU are both doing their job and keeping it so that the attacker running in this process cannot see the memory of the victim process and couldn't get at something like a private key, they both do share an L2 cache. The L2 cache is shared among the performance cores on Apple M-Series silicon. That means that any time the victim process does something that accesses the L2 cache, it creates a possible liability where the attacker can see that it did that through time. Now, how would that actually happen? The thing about caches is, when you're talking about fast caches like L1 or L2 caches, they usually don't have the luxury of just storing all of the data completely separately by the address that it's stored. That's how we would normally think about a cache in terms of software, right? We just store the entire piece of information that we're keying on, like the memory address, and then we store the data, and we can use it, we can use the entire thing. That's not the way hardware caches work because they're under a lot more performance constraints about how they evict things and how they store things. Everything has to be very rigid and predictable. So the way that caches are actually designed in L1 and L2, and in this case on the M-Series silicon they are, is usually by designing something called a set associative cache. Set associative cache is just a fancy way of saying that it's really not one big cache. It's kind of like a bunch of little tiny caches, each of which has far fewer entries in it. In this case, the L2 is what's called a 12-way set associative cache, which means that it's actually built up of lots of little 12 entry. Have I got enough for 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes. It's actually built up of lots of little 12 entry caches. And that's a weird thing, but that's just how it ends up working out. The 12-way in 12-way set associative means there's lots of little 12-way caches. How many? Enough so that they can store the amount that the L2 stores. If it's a 1 megabyte L2, it's enough 12-way caches to store 1 megabyte, right? Now remember, each of these buckets is a cache line size. So in the case of the L2 here, it's probably 128 bytes, because like we said in the M-Series, apparently, according to the researchers, it's 128-byte cache lines. So in the L2, we'd have 12 128-byte buckets to store things in one of these little cache pieces. So what's actually happening when you're using one of these CPU caches because of the set associativity is that really, it's only got 12 entries to store data for a certain type of address. Because there's all these little tiny caches, it's not really operating as one big cache. So it becomes important to understand, how does the cache know when you ask for a particular address, which one of these little tiny 12-way caches it's going to look in? Well, it breaks the address. So if I imagine this is a memory address here, it breaks the address down into pieces. Obviously, there's going to be some bottom part that isn't cared about here because we're saying that there are 128 bytes. So some of the bottom bits that tell you where, a memory address is byte granular. So the one that tells you where you would be byte granular inside 128 bytes, we throw those bits away, right? And then we've got some bits in the middle here. And what it's going to do is going to grab those bits from the middle and use those to figure out how it's going to index into its giant set of these 12-way caches. So it's really the bits that come after these ones we've thrown away here. These tell us which set right? This is what that's called, which set that we're going to look into for our 12-way lookup in the cache. And crucially, what this means is that any memory address with the same bits in here is going to map effectively to the same 12-way cache, small, tiny little cache inside the cache, right? That cache set. Now, there is one more rub here. It's not really that relevant for purposes of the attack, but I'll just mention it. Some caches have additional separation of things called slicing. And this is because you can imagine if you're just taking these bits here, sometimes you can end up with unfortunate collisions where lots of things map to the same cache set, and you want to try and improve that as a hardware designer. So sometimes what they'll do is they'll take other bits from elsewhere, and they'll mix those together in sort of a hash, and they'll use that to basically partition the cache up front into multiple slices, each slice having its own ways, and then you use these bits to index in there, right? So sometimes it's like a two-step data stream. First, you hash to find the slice, then you look inside a set. And again, this is just to try and make sure you don't end up in some pathological case. So the crucial part for exploits that involve cache timing is the fact that this number is really small. Normally, you wouldn't care because, again, you have to have these bits match and a slice bit match. There's all these kinds of things that have to happen by accident in normal code in order for you to somehow pathologically have most of your memory accesses all end up trying to be cached by the same 12-way set inside your cache. It's just the reason you never worry about this when you're normally programming is because it basically can't happen by accident. It's so incredibly rare. You'd have to accidentally have something strided exactly correctly and all of your accesses look like that, and it doesn't happen by accident very frequently. But the problem here is we're talking about an attacker. So once we're talking about someone who's intentionally trying to do something malicious, well, now all bets are off. Obviously, if the only thing that's determining where in the cache you're going to be are these middle bytes of the address that you were looking up, well, an attacker could clearly try to craft a set of addresses that all map to the same 12-way set. And if they do, right, they can pretty easily control an entire cache set by just making sure that they look up more than 12 things with those same bytes. And then they will fill up that entire way, right? Each way in this 12, the entire set, each way in the set, they will fill it up with data that they have placed there. Now, again, this may all seem very confusing because you're like, okay, so what? So they filled up the cache. Well, remember, all we need is some way to detect differences in timing. And a cache will return data much more quickly if something is in it than if it is not in it. So if an attacker can craft a series of addresses, which when it does the accesses, it knows will fill up all of the ways in this set, then it can time how long it takes to access those again, right? It just says, well, I'll do these 12 accesses and I'll fill them up, and then I will access it again, and I should get back those things very quickly because they're all in the cache. Unless some hapless victim process, for example, also were to access something that caused a fill in this cache set. If the victim process does something that maps to this same set and evicts one of the things that the attacker has put there, then when the attacker goes to look at them again, these are quick, slow, quick, right? So all of a sudden, the total time it takes to read all the stuff back that the attacker thought it put there suddenly takes a little bit longer. And we can measure that. So all of a sudden, the victim process, which thinks that it wasn't doing anything observable just by accessing some memory, actually was doing something observable. It was knocking a line out of a particular cache set that an attacker had controlled and can look to see that now getting back its controlled data that it put there takes a little longer because at least one of them, possibly more, has been evicted. And that's the only piece of information it really needs at that point. It knows you did something. So that gives them the basis to mount an attack, right? Now, this is not new. this is not part of the GoFetch paper's contributions. This is something that has been known for a while. When you look at things like microarchitecture attacks, timing attacks, there's a whole range of cache attacks. And this entire process right here falls under a particular name called prime and probe. The prime part is we fill this up with data that we control. The probe part is we then see how long it takes to read the data back, and hey, if it takes too long, we know someone else has been in there, right? So that has been used before for security exploits. This is a known thing. And so what's so fascinating about this particular GoFetch attack is the things they are attacking are hardened against this. The really interesting part about this new DMP-based exploit is that even though the code has already been modified by the security communities, all the important cryptographic code has been modified to guard against prime and probe, the DMP is going to screw things up. So let's see how that works. Okay. What they do in the paper is they give a series of escalatingly more complicated attacks. So they show how to attack things like RSA, like Diffie-Hellman key exchange, post-quantum crypto. They've got 4 different attacks that are actual attacks on things, the whole scheme, right? Where you get private information or you reveal something that should not be revealed. But what they start with is actually something much simpler so that you can understand just the nature of the attack and you don't have to focus on like, okay, how did we make that attack this particular piece of code? And so what I'm going to do is go over that now because it's really, really interesting to see how it works. And then you can kind of imagine how you then use this to leak bits of other kinds of schemes that also have this structure. So what they do is they describe CT swap. CT swap is something in OpenSSL, and it's a very simple basic primitive that you can use. And the CT in it stands for constant time. Remember what I said. This is for attacking things that have already been hardened. So CT swap is something that someone has hardened. It's a swap that will swap 2 arrays based on a secret value, right? So the secret value is either yes, you should swap, no, you shouldn't swap, that you do not want to reveal to anyone on the outside because of timing, right? You don't want them to be able to see that you did a swap or not. Now just think about this. If you or I were writing a swap, we might just do, well, okay, if you want to swap or not based on a Boolean, you just say, if the Boolean is true, go through and do the swap. If it's not, don't do anything. Problem solved, right? That is not constant time. That will leak information like a sieve because all of the work is only done in the case where the secret is true. So all an attacker has to do is measure how long we took to do things, and it will know that anytime the secret's true, it'll take longer. Really simple, right? So constant time is the way that they try to harden things against these kinds of like prime and probe attacks. So if we have some kind of a Boolean, right, which is like we should swap, and then we have 2 arrays, A and B, and those arrays should either have their content swapped or they should stay the same. The whole point behind constant time cryptography or constant time programming is that we're not going to change how many operations we do. We have to figure out a way to do the swap so that we do not leak any timing information. And that is how CT swap is written. It is properly hardened. So what it does is it says, okay, first we're going to make a mask. And we just need a mask that's going to be all 1s or all 0s based on the value of swap. I think they do that by doing like swap -1 knotted, right? So if swap is 1, it'll just be 1 minus 1, which is 0, knotted, which is all 1s. If swap is 0, it'll be 0 minus 1, which is all 1s, knotted, which is 0. So it's just basically a way of turning a single bit into all 1s or all 0s. That's it. But you could do anything here as long as it's constant time, right? You can't put an if statement. Don't do something like that. We're trying to be constant timers, so just do an operation. Next, we're going to loop over all of the contents of these arrays. So we're just going to do like a for I loop here. And we're going to operate on every single value in the array every time, right? We can't do an if. We don't want to do anything that could change the amount of time it takes us to do stuff or changes the cache or anything. We want to keep everything so that we read and write all the same values into the same number of operations. So first we compute a delta. That delta is defined as the ith value of A XORed with the ith value of B, ANDed with the mask. So this will just produce either A XOR B if the mask is all ones, or if the mask is all zeros, it just produces 0. So this is delta is either 0 or A hat B. Then we produce the swap, or not, by just doing AI XORed with the delta and BI XORed with the delta. Now again, that works because in the case where we're not supposed to swap, this is just going to be 0, right? So AI XORed with 0 is just itself. BI XORed with 0, also itself. So we don't swap. Mission accomplished. If the mask is actually ones, then it's AI hat BI in delta, right? A hat B. The A's cancel and we just get B, which is what we wanted. Opposite happens here. B hat A hat B. The two B's cancel and we just get the A. So this accomplishes our constant time swap. And notice we are always reading AI once. We are always reading BI once. We are always writing AI once and reading BI once, right? And we're always doing the same number of XORs. You would assume it doesn't get reread here, right? So it's only going to be loaded once and then reused in two different places, right? So this shouldn't leak anything. But as the researchers show, thanks to the DMP, it actually does. This value is supposed to be a secret. Not only is the attacker who, is going to call this function indirectly, basically, not supposed to know what the value of the secret was, there also are never disclosed the eventual values of these arrays. So anyone who asks for something to happen and has CT swap get called is never supposed to know what the value of this secret was. Now you can imagine the actual situation in which this would occur. CT swap is like a primitive inside OpenSSL, so something where the attacker calls and asks for a message to be signed or to validate something or whatever's going to happen, and something in that code calls CT swap, and this comes from part of the secret part of the crypto, right? The attacker who's watching should not be able to ever figure that out. It's never going to get told. It's not going to have these handed back. It's just passing in data that's going to go in through these, that's going to have operations happen to it, but it's never going to see the results. So it should never be able to figure out this secret value, and thanks to constant time programming, it won't be able to figure that out just by timing. Unless the crafty attacker figures out a way to use the DMP to change this constant time operation into one that won't be quite so constant time. So how does it do that? Well, in this attack, like I said, these arrays are things that the attacker provides on the outside, right? They're part of the source data that gets fed in. And this is the thing that's being kept secret. So if the attacker can provide values that go into A and B, well, normally it wouldn't matter. You couldn't change the amount of time of anything in the system just by putting different data in here because it wouldn't matter at all. However, with the DMP, what would happen if you were to stuff something that looked like pointers into A and B? All of a sudden, secret memory accesses that the person who wrote CT swap never anticipated are now going to happen. Anytime the DMP wakes up and looks at one of these things that you've loaded, because say it gets pulled into that L1 cache, right? If it looks at it and sees something that looks like a pointer in there, it's going to load it into the cache. And as we just saw, if you can mount a prime and probe attack where the attacker has controlled a cache line, if they know which cache line would have something evicted by that DMP load, they can probe and find out that you did that. Now, it's still a little confusing, right? Because, well, what difference would it make? Suppose I wanted to figure out, whether this was going to happen. So I stuff something that looks like a pointer into B, and I don't stuff it into A, or I stuff it into both of them, or only into A and not B. Well, no matter what happens, right? it's still going to have the DMP access that pointer and load it. It should be the same in all circumstances, right? There shouldn't be a way to leak timing information from that. Well, here's the thing. The attacker doesn't have to wait until you're done. The attacker can be running a prime and probe attack the entire time. So imagine this scenario. The attacker runs something like prime and probe continuously. It kicks off whatever, request that was for message signing or whoever you were going to use, whatever CT swap was getting called for. It kicks that off and says, hey, could you do this for me? And the victim process says, sure, I'll get started on that. Meanwhile, the attacker process sits there and says, okay, I'm going to keep evicting a cache set. I'm going to use my eviction set. I'm going to keep probing it, right? Evict everything from it, probe it, see how long it takes, evict everything, probe it. I'll just do that continuously. And then it has data for the entire runtime of this process. It can see what's going on during this loop, not just after it completes. So let's suppose we know we can evict the A array, the actual array itself. We know we can control the cache line that A is going to be in, and then we can also, furthermore, know we can control some pointer that we're going to stick in here. So we have two things. We know we can control the cache line for pointer and the cache line for A. We know we can control those. So we can evict them, and we can time how long it takes us to access them so we can see whether anyone has accessed it. Well, now, think about what happens when this loop executes. If this is 64 bits, right, which is how big the registers would be in here that were doing this, in one cache line, how many of those are going to be? That's 8 bytes, right? So we actually have the same thing again, where we've got 8 entries in that cache line. Let's suppose that I am going to swap. So here's the A array. Now the B array, I do exactly what I said, and I fill that full of pointer. It's just all in there. Now, I know that the DMP won't look at the contents of B at all after the first time it pulls those into the cache line, right? After it pulls that into the cache. Because it's going to have that do not scan hint. So B, I just never intentionally evict. The attacker process never tries to evict B. It lets B stay in the cache and stay tagged do not scan. So even though B contains pointer, it won't be screwing up our results because the DMP's never going to scan it again. Once it scans it the first time, it won't do it again. Now we come to the loop, and what happens if swap was true? Well, now, as it marches through this for I loop, right, it will have brought A into, this has to get brought into the cache to start working with it. And it doesn't have pointer in there, and it will get tagged with a do not scan hint. So it seems like our attack isn't working very well yet. However, as this routine marches through, it's going to copy pointer into A if swap was true. Pointer, pointer, pointer. Each time through the loop, I go one more further. If our attacker process is sitting there constantly running prime and probe, so we're evicting A out of the cache again, right? We're forcing A out. Then when we succeed in forcing A out, it will lose its do not scan hint. Now, on the next loop through the next time through this for I loop, when it goes to read this value, right here, boom, it's got to pull in this cache line. The DMP will wake up. Should I scan it? Yes, I should. It doesn't have a do not scan hint anymore. What do I find in here? A bunch of things that look like pointers. So I dereference them. Now, of course, it is a bit tricky. These pointers have to have fallen out of the 128 byte window, so we have to have handled that, right? We have to be evicting this thing constantly both A and pointer, right? We have to make sure that those are outside of they have to be flushed out of the cache so that we know that A will get brought back in so that it can be rescanned. And we have to know that P is not in the cache because we're going to be timing that set and watching for it to come back in. So we have to make sure that has also been properly evicted. All of that stuff has to happen. But we can do it by just sitting in the attacker process, making sure that we keep hammering on those addresses to force all the eviction, and then just constantly checking to see if we get everything back as quickly as we thought, which means that no swap has occurred, or if suddenly it takes longer to get the data that we stuck in there, and if that's the case, we know the swap has occurred. Now they draw a little diagram in there. It looks like this. It's not perfect. It's basically a distribution where the timings, right, here is faster. This is in the case where the swap didn't occur, and here is slower, right? But it is remarkably little overlap. So it's a fairly reliable actual attack because most of the time you're going to get a fairly reliable answer, and the amount of times you have to run it to distinguish between the small amount of overlap you might get is not that high. So it's actually a fairly practical attack at the end of the day, at least according to the diagram that they showed for this kind of leak. So that is how the attack actually works. Constantly flushing the cache, waiting for the DMP to wake up and read it back in, and if a pointer has moved, there you go. Now, like I said, they build on this exact same concept to attack more sophisticated schemes. And if you like this sort of stuff, you can go read those explanations. With this in mind, you can go read the explanations in the paper for more detail on those schemes, like the RSA attack in Go, the Diffie-Hellman exchange, and the two post-quantum ones they did. And I would imagine that other people, now that this has been disclosed, will probably find other exploits as well using the same kind of attack. Okay. Now, there is one more thing I need to mention here. Throughout all of this, it may have been a bit confusing because at the beginning, we already said that macOS and like the CPU architecture itself are correctly, distinguishing between the memory addresses of the victim process and the attacker process. So throughout all of this, when I say if you can control a cache set and you evict it, right? The question might have come up in your mind, well, how can you know? How do you know which cache lines to evict? Because you're in one virtual address space and the victim's in another virtual address space. You can't know, right? You can't tell what you're doing. You have no idea which cache sets you should be evicting and watching, right? Well, once again, and this is not new for this paper, but this is just something that you learn, I guess, if you're a security researcher. It's news to me, right? These are not things I normally think about. But it turns out, well, if you don't know because you're not in the same memory space and you just need to make sure that you're evicting the same cache set as would be evicted by the victim's addressing, right? It doesn't really matter. What we can do is just spend a bunch of time before we actually mount our attack doing timing queries using different addresses, and we see which ones get evicted, right? So actually, there's an entire step that they do at the beginning, which is about, I think they said it was around 2 minutes, if I remember correctly, where they do nothing other than ask for things that will trigger the target code to execute after they have done some priming and probing, right? And they do that on specific cache sets, and they look to see which ones are being affected. And in so doing, they build up what they call eviction sets that they know properly map to the cache sets that they need. So even the fact that these are different virtual address spaces and this attacker can't know the virtual address layout of this victim process, right? The attacker doesn't know that. It doesn't matter because the same timing leaks that you're going to use for the attack can help you build the eviction sets before the attack. It really is mind-boggling. One of the reasons I wanted to make this video is because I had to go through and understand all these things. They're all news to me, right? I think probably if you're a security researcher, a lot of the stuff in the paper, because the paper just glosses over a bunch of these things, right? A lot of the stuff in the paper is not news. You already know about building eviction sets. You already know about prime and probe. You already know these things. So, you're just like, okay, I see. They took prime and probe and eviction sets. They built the eviction sets for the prime and probe. That they did that. And the part about the DMP that's interesting is the fact that it's going to wake up read this cache line. So we just have to have this extra pointer. So we're evicting both pointer and the normal cache line that we're evicting to force it to reload it. Okay, I get it, right? I'm imagining a security researcher probably reads the paper and it's like, okay, cool. I get the new thing, but, I didn't really, think the rest of the stuff is just stuff I already knew. For people like me, and probably a lot of people watching this, right, we're not used to dealing with that. I've never written any code to build an eviction set, right? In normal programming, you'd never have to do that sort of a thing. Even when I've done things like cache testing, you're in the same memory space. So you can just craft an address that has the bits that you need, and you're done. You don't have to try and figure out which bits you would need to set in order to screw with someone else's memory space that they're using, right? So that's it for the GoFetch exploit. Like I said, not a security researcher, cannot tell you anything about the severity of this exploit. However, what I can tell you for sure, after having gone through all of this, is it doesn't require any specific elevated privileges or anything like that, right? All you really need to be able to do is run an attacker process, and that process does need the ability, for example, one of the things I will mention that's not related to any of this is it does need a high-precision timer, but they made that high-precision timer just with a separate thread that sits here and inks a variable, right? Because they didn't rely on having any kind of administrator privileges where they could access actual Silicon high-frequency timers. So it works if you have the ability to create a fairly high-frequency timer by creating a separate thread that inks a variable you can inspect, which any normal native app can do, even with no privileges. But I'm not sure how well that would work on something like JavaScript, for example, right? So it remains to be seen, I think, and we'll have to wait for other security researchers to really let us know how dangerous this exploit actually is. If it turns out you can mount some of this from JavaScript, that could be really bad. If it turns out it has to be a native app, it's maybe not quite as bad because unlike things like Spectre and Meltdown, which were targeting x64, to the best of my knowledge, M-Series Silicon isn't really used in, server farms or things like that, where you're likely to be running multiple different people's programs on the same thing in isolation, where this attack could be really dangerous, right? So, yeah, I don't know. I really don't know how to opine on that. So I think, unfortunately, I just have to say, not being a security researcher, you're going to have to wait for some people to really study this and weigh in on how severe this exploit actually is in the wild. And again, I would say I don't think M3 is implicated. So the very latest Mac Silicon has the proper way to turn this off. So it shouldn't really pose too much of a practical problem for M3s. It's only M1s and M2s that we're really talking about. And how severe it turns out to be on those, and maybe it can be turned off on those in some other way, et cetera, we'll see. All of that, you'll just have to keep watching the tech news on it to see when there's more disclosures. I really couldn't tell you. So that's about it. I hope you've enjoyed this. I know I had a lot of fun reading through it, and it was very subtle. I had to read the paper multiple times to get everything, and I had to go back and read references to get everything too. There was that much stuff in there. So I hope you've enjoyed it, and as always, if you like this kind of thing, it's what I do on my Substack over at computerenhanced.com. We go over all sorts of stuff like this. We're talking about set associativity right now, actually. Not from a security standpoint, because that's not what I do, but just from a microarchitecture understanding and performance standpoint, which you have to know these sorts of things for that as well. The domains overlap quite a bit. It's just we're trying to do different things with the microarchitecture knowledge than security researchers are. All right. Thank you for joining me. Until the next video, have fun programming, everyone, and I'll see you on the internet.